How are thermodynamic properties measured in the laboratory? Have you ever wondered how scientists measure things like temperature and pressure in the lab? It's fascinating how these measurements help us understand the world around us. Let's break down how thermodynamic properties are measured in the laboratory. First up is thermometry, which is all about measuring temperature. Devices like thermocouples and resistance temperature detectors are commonly used. These tools help scientists get accurate temperature readings, which are essential for experiments. Next, we have manometry, which measures pressure. This is often done using devices such as mercury manometers or digital manometers. These instruments help researchers understand how pressure changes in different conditions. Calorimetry is another important technique. It measures heat transfer, specifically how much heat a sample absorbs or releases. This is crucial for studying reactions and phase changes in materials. Now, let's dive into some specific calorimetric techniques. Differential scanning calorimetry is a popular method. It heats or cools a sample while measuring the energy changes compared to a reference. This helps identify phase transitions and specific heat capacity. Then there's thermogravimetric analysis, which looks at changes in mass as temperature changes. This technique is useful for studying how materials decompose or evaporate. Simultaneous thermal analysis combines both differential scanning calorimetry and thermogravimetric analysis. This method provides data on heat flow and mass changes at the same time, improving accuracy in measurements. When it comes to thermal conductivity, the transient plane source method is quite effective. This method uses a thin spiral heater placed between insulating layers. It applies a brief heat pulse and measures the temperature response to calculate thermal conductivity. Steady-state techniques are also used. They apply constant heat until the temperature stabilizes, then measure temperature gradients to determine thermal conductivity. Another method is the transient line heat source, which applies heat through a small needle heater for a short time. It measures temperature changes to infer thermal properties dynamically. Advanced techniques like spectroscopy provide molecular-level information. Techniques such as Raman and infrared spectroscopy can give insights into energy states and structural changes. Nanocalorimetry measures heat transfer at the nanoscale, which is particularly useful for studying tiny materials. Microelectromechanical systems and lab-on-a-chip devices integrate multiple measurement functions for precise data collection. Finally, advanced data analysis techniques, including machine learning and artificial intelligence, help improve the accuracy of thermodynamic data interpretation. These measurements are not just academic, they have practical applications. In material science, they help understand stability and thermal performance. In engineering, they guide the design of energy storage systems and thermal management. In biological studies, they reveal how organisms respond to thermal changes. By using these various techniques, scientists can measure thermodynamic properties accurately, making the principles of thermodynamics accessible and applicable across many fields.